Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So a change of pace, back to nuclear science. Energy is just such an important subject, the whole kinetic energy thing. You don't get that right, just everything goes wrong. And you could sort of argue there's these key things in physics. The double slit experiment inadvertently led to this wave theory, which led to, all kinds of, nonsense from like Dirac, that all of a sudden electrons are waving. They're not even particles anymore. They're not things with these little tiny properties. And so, they've just made a mess out of everything. With just the, one thing, they draw a conclusion. Once they draw that conclusion, everything's just ruined. So obviously they have no force. They have no understanding of why electrons and protons repel and attract. Okay, so I've clearly created a simple model. All you need is absorption, reflection, and transition of a, elemental force that goes at constant speed. And it just has two properties. There's electron force and there's proton force. And that's it. Okay, yeah, electron and proton force, electron force, and they have an inverse relationship to the force. And that simple diagram creates this obvious pattern you can notice, where electrons and protons attract to each other and repel. Protons repel protons, electrons repel electrons. So, and it works, and it's so simple. So I'm not saying people should have thought of this on their own. I'm just saying they should have thought that, well, maybe there's some explanation that isn't extraordinary. That it's not just that they have some sort of magic powers, that there's actually a physical mechanism that causes it, and the physical mechanism will be elemental and simple. And in fact, an elemental and simple explanation does work. And it does, it does surprise me that there isn't any curiosity, there isn't any capacity for people to, again, this is sort of a cliche, but to think outside of their indoctrination box. I mean, just no capacity. I mean, they're not even the slightest bit curious to hear a better explanation than just wooey, it just happens, it just does, it just blah blah. So anyway, Jason of Math and Science is going to give the standard mush explanation for what happens inside of nucleuses, and it involves something called the strong force. So the argument is you can't get protons close to each other unless they invent some fake force to pull them into that circumstance. And I would just say, obviously, I can get two protons really close to each other by just sticking an electron between the two protons, as you can see here. And the only issue is that if there's any noise or unevenness in that background field of force, that is, any nuances created by other electrons and protons, they won't line up perfectly because of that noise. And that the less noise, that is, the more consistent their environment, the more rigid their geometry becomes. So, you go from this Mickey Mouse kind of idea to the idea that, yes, it would just be a very rigid geometry like you understand a magnet to be, where magnets, if you must know that much physics, that magnets are made out of little magnets. Like there's little dipoles, and the little dipoles are all lining up in the same direction, north, south, north, south, north, south, north, south, north, south. And that's why you can just break a magnet anywhere and you get two new magnets, is because you're cleaving it on those little magnets. You can't break the atoms, you're only breaking the separation between atoms. So the atoms are all oriented north, south, north, south, north, south. So no matter where you break it, you got north, south still. All right. I mean, this is, I really shouldn't have to do any work anymore, because you should all sort of be celebrating, hey, we actually have a reasonable, scientific, physical explanation for reality instead of this wooey mush. But no, alas, that's not happening. You're going to resist all the way. You're going to have to be humiliated out of humiliated in the sense we're going to have to go where the evidence is going to be so obvious and so dramatic, and it's going to be, well, why did that take forever? I mean, how much Darwinian facts do you have to have before you accept evolution, kind of thing, and you're just going to look ridiculous. That, we had to pile on geology and biology and chromosomes and chemistry and fossils, and you just won't go there until we get all of that big pile of evidence. It just demonstrates you're just fanatics for religion now. You just have some belief system that, some mommy figure told you, and that's all you know. It's pathetic, frankly. You're just humiliating your neural capacity. Frankly, at this point, that's all that can be said, is that you're humiliatingly ignorant, and you really don't even understand the concept of science and what it's supposed to be. All right, with that premise, leave us begin. Play button.
Out the nucleus of the atom for a second. So you know that there are protons in that nucleus, and there's also neutrons in that nucleus. And if you look on the periodic table, you can figure out exactly how many of each are in every nucleus of the atoms that we know about.
So the disappointing part, you can't even do that anymore. Periodic tables have gotten incomprehensible. But anyway, it used to be they just gave you a weight, and then how many electrons, how many protons, how many orbiting, Anyway, but no. So the whole concept of the neutron is the problem. So I would argue, as I show in the simulation, the neutron is just an electron and proton really close to each other. That's the simple answer. Neutrons are electrons and protons, and there's no point in calling it a neutron. It just happens to be that there's two ways you can encounter a proton and an electron. You can encounter them individually, or you can encounter them as something close to each other. And the fact is the noisier the field they're in, the more likely it is they're going to be stuck together. I mean, the more unlikely they'll be stuck together. And the more pressurized their environment, the more likely they're going to be very close to each other. And it's just a simple kind of almost gravity argument that the more gravity, the more compression. And so yes, neutrons are more likely to be experienced, inside of nucleuses, and they decay, as they use the word decay. But I'd argue it is really not decay, it's just that they can't survive outside of the high pressure environment. So you could almost argue that it's sort of like there's a lot of deep sea critters that you can't bring to the surface because the pressure, changes so radically and they just explode. So you have to put them in a pressurized container, and then bring them to the surface. But anyway, they just don't bother doing any reasoning or logic here. So it just seems kind of obvious still. I mean, I could show you Feynman saying it's made out of an electron and proton. I could show lots of scientists saying, yes, neutrons decay into electron and proton. So it's just sort of saying to you it's made out of electrons and protons. So let's not even bother calling it a neutron. Let's just count how many electrons and protons are in the nucleus. So what the basic trend is that there's always going to be twice as many there's going to be close to twice as many protons as neutrons. That's the usual balance. And then as the atoms get bigger and bigger, they can end up with 110 protons and 53, some number that isn't quite 50-50. So they'll end up with a few more protons than they will electrons in the nucleus. In terms of the 2-to-1 relationship won't be perfect. So the idea is there's 2-to-1. For every one electron, there's 2 protons. Continuing.
The protons themselves are positively charged in the nucleus. And if you remember, positive charges like to repel each other. So that means...
So again, you're just saying, who are you talking to? I mean, these videos are so uneven, in terms of, you're just insulting anybody who's more than 12 years old.
means, and the neutrons don't have any charge. So that means in the nucleus,
So obviously the neutrons do have a charge. From a distance, red and blue will look like purple. Up close, you'll see the red and blue. So the simple explanation is it's neutral from a distance. A magnet is neutral from a distance. You can't, there's no magnetic field essentially because the two dilute each other. But the closer you get, the more magnetic, okay, the more you'll see the poles.
all of the protons are trying to be forced apart from each other.
Right, so all of the electrons are doing exactly the same thing. So yeah, that's just the simple principle, but that inverse part is really important. The fact that they're very attractive, they're just as attractive as they are repulsive. So the electrons hate the electrons as much as they love protons, and vice versa. So, there's no point in talking about a strong force one way when this force is just as strong the other way.
So have you ever thought about it? Why does the nucleus stay together at all? Why doesn't it just explode?
Because you don't understand what a neutron is. That's that's the simple explanation. If you just understand that a neutron does have an electron in it, then you understand why protons hang around. Is because they're attracted to the electrons that are in the nucleus. I mean, Rutherford thought of it that way. He didn't think of neutron as some kind of object that now destroyed the need for there to be electrons in the nucleus. He understood the nucleus to have both positive and negative charges and to be net positive. That is, it has more positive charges, but it still has negative charges.
Because they're all positive charges, the neutrons don't have any charges, and they're trying to...
So he keeps saying it, neutrons don't have any charges, when clearly they're made out of charges. It's the first dipole.
To force themselves apart. So how does it stay together? And the answer to that is there's an even stronger force than that electric repulsion.
So something new just made up. So they just made up some nuke thingy. Okay, so there's a north and a south pole in magnetism, and then there's Holy Ghost magnetism. There's the Holy Ghost function. They just made up a completely non-tangible, non-physical mechanism that somehow does this magical thing of just saying, let's drag two of these red things together, right? So, we'll just take two of the things in the environment and we'll somehow force them together with just the magical mechanism. Do people think that's a satisfactory explanation? Just an invented, contrived, do what we say, do what we want, made up mechanism. There's no physics at all.
And that's called the strong nuclear force.
The big invented pile of crap is what it could be called. Just a completely contrived magical mechanism. The completely contrived magical mechanism. The cartoon is suitable.
And it's one of the four fundamental forces of nature. Now that...
So they've made it something fundamental, so something you'll never see, and something that doesn't have any physics. It doesn't made out of anything. It isn't even, their idea of a gluon that might be a creator of the force is the idea is it runs to you, sticks a string on you or something, that runs back and then pulls the string. These are the silliest possible explanations. I mean, it's really roadrunner moronic. And you're just like, how could this be physics? This is something a scientist cooked up? This is embarrassing. Humans can't do better than this? Shit.
Force is millions of times stronger than that electric repulsion.
So again, you don't need anything millions of times strong. You don't need any of that. All you need is an electron. You want to collect some protons? Just stick an electron somewhere, and you'll collect some protons. No problem. You want to get if there were, obviously there are magnetic monopoles. They're called electrons and protons. I mean, the electrons and protons. Magnetism is just a consequence of the arrangement of electrons and protons.
Propulsion, so it can hold the nucleus together.
So it can do it with its magical can-do powers.
but it only acts on very short distances.
And but it has all kinds of conditions. Yeah, so it doesn't even do the magic thing like in a straight line. It's got all kinds of crookedy conditions. Well, it has to walk with a cane, and it has to take vitamin pills, and it has to do, I mean, it's just so ridiculous. A conditional magical force.
So it only really acts inside the nucleus of the atom.
So, again, well, says you. So how's the magical force know where the outside of the atom is or the inside of the nucleus is? How does it know any of that? Too ridiculous.
It doesn't really reach across the universe like a proton here and a proton here. You can feel
So we know that all these forces don't actually reach all the way across the universe. It's just that they have a component that theoretically is possible that could arrive at the end of the universe. But say my light bulb, if I turned it on here, 15 billion light years away, you're not going to get any photons, okay? It just ain't going to happen. You're going to have to go across, terabytes of acreage before you're going to be anywhere close to getting one photon collected. So, and then as I just pointed out, the magnetic forces are sort of moot at a distance because you're getting just as much north as you are south, and whatever you're affecting, it's invisible now. The something can only collect red and blue. It can't collect purple.
Force between them. But inside the nucleus, it's millions of times stronger than anything else, so it holds.
Oh, yeah, so just baby talk. Magical force, it's just baby talk.
Holds it together. Now, here's the thing.
So, okay, I might as well just draw now and save myself a little bit of trouble. Simple explanation works. And then, this gets into, so I did do some thinking about the chemistry. The chemistry of nucleuses. Yeah. And it's sort of, it all sort of fits together. It's just a little bit, there's always a little bit of a hole here or hole there in terms of being a perfect explanation for anything. So the simple idea is that the protons are attracted to electrons, and they are attracted based on how they see each other. I would make that obvious argument that it's about what you see. So magnets see each other, okay? They create a field, okay, and the field makes it possible for them to see their differences. And so they have to be lined up, they have to be oriented in a specific way to see the field. And the same is true for electrons and protons. So I would argue that they are of the same size. And the trick is that the proton is more massive, let's just say, or there's less proton force in the environment, whatever it is, but they tend to be heavier. I should have drawn this exactly the opposite. Is it worth fixing? Oh, let's fix it because we're conscientious that way. Alright, so I'm the right color. Yes, electrons are associated with a negative or ground type charge, where the protons are associated with the positive or plus. So obviously that's just in our brain, but it's not. The two things are equal players in a game, okay? But anyway, so you gotta understand that you don't need a strong force. The electron has plenty of ability to attract protons as long as the protons can't see each other. So that's the simple argument, is if this is a force that's being thrown, photons so to speak, between them, then yeah, they're not going to have any problem. Once they can see each other, then there's a problem. They can't see each other, there's no problem. They could just be on either side of an electron, like Vulcan could be on the opposite side of the sun and we could never see it because it orbits at the same speed and blah 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 blah. But anyway, the simple argument though is, so if I put a little bit of noise into the system though, there was extra photons coming one way and a little extra going the other, and they're jiggling, though those protons are going up and down, or the electrons going up and down here, moving, jiggling. Then you can understand the protons will end up seeing each other. They'll pop up and, oh, I can see the other proton. So even if I did it with magnets, plus and minus, had them north-south and north-south arrangement, stay there. You could understand it. Yeah, I could put the magnets in those kind of arrangements, and then if I was able to jiggle them, that very thing would happen. It would fall apart. So the idea is that when things are super cooled in other circumstances, you get a very nice arrangement of electrons and protons, and when they're hot, they're doing a lot of this, and that's causing them to expand and not be as coherent in the pattern they produce. So that's just an extra bit I'm just throwing in. The other point I've made is that you could sort of understand that in a nuclear reaction or some other circumstance where you have a gamma ray or some other piece of high energy photon, you could easily give enough momentum to the electron to knock it out of its position. So if I had a stack of magnets and I could hit one of them hard enough, quickly enough, with enough energy, I could just pop it out and the rest of them would just reattract and that will pop out. But if I apply a force slowly, I could almost never pull them apart that way. So you have to apply the force in a certain way to get things to happen. And that's obviously the photoelectric effect and other effects where you have clearly it's all about speed. And the more energy in the shorter amount of time means a higher acceleration. And if I accelerate that electron quickly, I can knock it out of there. And then I have two protons that are insanely close to each other. Okay, they're in a position they could never get to from the outside world. You could never, if I took two protons without the electron there, I couldn't get them that close because the repulsion would be so strong that you'd need a really incredible force to ever get them that close. And but like I said, all I do is pop an electron in there and I solve the problem. Now, as I was going through this, to understand the formation of nucleuses, so helium's interesting. Helium-4, they call it, right? So what color do I have here? What the hell's wrong with this pen? Already failing me? That's pretty dismal. Is it the wrong one? Yeah, well, let me fix this. Strange. Alright, well, we'll see how long this one lasts. Anyway, so it's in this case we have 4 protons and 2 electrons, and I would argue that it's a case where the same things that I'm showing in the simulation are forming. These things kind of like a deuteron, okay, where you have a proton and you have an electron. And the trick of the helium is being created in the high pressure of the sun is that the electrons are being pushed together in this case by the arrangement of the protons. So the protons and the electrons are obviously if this proton can see both these electrons, obviously it's going to be very attracted. If this proton can see both these electrons, it's going to be very attracted. So you can understand that there's a lot of pressure pulling this thing together, even though it has these repulsive forces between all the protons. And so that's the nature of helium. And so then you go up to lithium and eventually get to carbon. So I'll just draw carbon because it just, based on this model of understanding that it's just about, really building it out of the pieces of a helium. So everything is made out of helium, sort of, is a decent enough explanation. So that's 12. All right. So carbon 12, that's the standard carbon if you had just protons. And obviously to make that work is pretty simple. You just put electrons in here and you've created a solution to that problem. Now the problem is that's only 6 electrons. So the trick is that there's 2 electrons being stuck together here, in the sense that I have to place. You just understand that the mutual attraction between the fact that there are two electrons here are pulling the protons, and they're forcing the two electrons to be closer to each other than they would be. And then the simple explanation for carbon 13 would be the extra proton right in there. Okay, so and that's the unstable one, because this is even, you have an electron proton, you have electron proton electron, but you have it inside of this stable 5 dice thing. The 5 dice thing is very stable. All right, so I just thought the idea that it does work as a building block. So you can go to lithium, which is a more it's just another version of this. Well, you've added, my mistake there. So you're adding another electron and 2 more protons. Boy, those pens are disappointing. Yeah, instantly run out of ink. It's like instant. All right, there, and then you'd have 2 more protons. And you can go right up the ladder. Beryllium, boron, and then you get to this more complex carbon. Now the thing about the carbon is that it has the extra, make sure I have the right pen, you have the valence electrons. So these are the electrons that are technically the orbiting electrons, and you can see that these places are perfect because you have all this positive here. You have proton, 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 which would be a really strong attractor of electrons. So these 4 electrons would be the 4 valence electrons, and then you can understand, once you've established those, any slight distortion in the symmetry would mean that yes, the other electrons, the 2 extra weak electrons, would be out here. So you have these 4 for binding with something, and then you have these 2 weak ones at a distance, and so it all kind of fits. It fits with also the idea that all of the metals, and especially carbon, it's understood to be a kind of a 2-dimensional molecule, so to speak, atom. The idea is it creates little wafers. It's layers. You can, what's the word they use for being able to fracture something on planes? Shit, I hate this vocabulary thing with age. You can, I'll think. Well, not coming to me. So anyway, it's like flaking. So anyway, these are like flat things that are sitting, and they slide right over each other, but they're almost like magnetically repelled, and so they just kind of float across each other. Very low friction. So in the form of graphite, carbon is a really good lubricant, and in the form of diamond, you can just you can hit it and cause very flat surfaces because the atoms are connected strongly, bound strongly as flakes this way, but they don't bind flat surface to flat surface. And then you could sort of look at this lithium, and you could just say to yourself, yeah, you can get why this is good for electrical stuff, because all the protons are ending up lined up, electrons in the middle. I mean, it sort of makes sense. It would be a good conveyor or controller of electricity, blah, blah, blah. So you can see some connections. Okay, I haven't gone through the whole thing yet and all that kind of crap, but I'm just saying as a preliminary statement, it works fairly well. Mostly. What color is this? Yeah, the red is dead now too. Bizarre. Alright, so I have to get different markers eventually. Anyway, so maybe we'll go back to the video and finish that. Alright, continuing.
Protons are in the nucleus and neutrons are in the nucleus, and they both generate the strong nuclear force holding it together.
All right, so they both generate the strong force. So again, this doesn't make any sense. At least, they used to even say that the strong force was obviously external, but it's clearly only doing this to things called protons. And so then he sits there and says the electrons are generating it. It just, what is that? Doesn't make any sense. I'm not gonna play that again, right? What the sense does that make?
Here in a proton here, you can feel a force between them. But inside the nucleus, it's millions of times stronger than anything else, so it holds it together. Now here's the thing. Protons are in the nucleus and neutrons are in the nucleus, and they both generate this strong nuclear force.
Okay, so they're saying the neutrons generate the force. I mean, so something that's completely different than a proton, right? It somehow generates the same force. I mean, it just doesn't make any sense.
Holding it together. So you
can't even figure out how exactly would some neutral thing even get in the nucleus. How would it be pushed or moved at all? So you lose all kind of coherency when you create something called a neutron, okay, that is truly neutral. Because then how does it get pushed around by anything? It doesn't get pushed by anything. So how could it ever even get into the nucleus?
Some neutrons in the nucleus to thin out the protons and generate enough of that strong force to hold it.
So again, it has to, the neutrons generate the magical force that magically pulls protons together. Again, I don't know why this is even a useful bit of gibberish. I mean, why do people fall for this? I mean, it's just such a vacuous statement about the reality. It's just obviously made up, like pixies, and then the Smurfs show up, and SpongeBob, and the Flintstones. I mean, it's it's childishly fake.
Together. But here's the problem. If you have too many neutrons, then what's happening is the nucleus gets too physically large.
So again, the largest is just electrons and protons. So you're just saying that for every neutron, you just say that's an electron and a proton. So you'll always sort of get the idea that there's twice as many protons as there are neutrons, because there's two proton. There's a proton and electron. There's a proton in the neutron, and you have one electron. So for every, you get it, there's twice as many protons as there are electrons in the nucleus, generally speaking.
For that strong force to hold it together, because remember, the strong force only acts over very short distances. So if you make a nucleus...
So again, any force only operates over these short distances. That's the inverse square law, frankly. So, I mean, and then you can have, in the case of magnets, you got a cubed law. So, I mean, obviously you can have a lot of forces diminish in their strength rapidly. So the same curve could be drawn for gravity, in the sense that it's it's quadratically decreasing in strength with distance.
With too many neutrons, it becomes what we call unstable, and it begins to.
So that's not what the argument is. It's not about how many. It's about that form, and the idea is that you can have an arrangement of protons and electrons where there's the opportunity to make it unstable, in the sense that one of them can jiggle a little too much and the whole thing falls apart. And that's all you're really saying is that because of the fact that I've diluted the force by putting an electron, proton, and electron inside of four protons, that you could argue that now I've made it more unstable, because any variation in that electron means the whole thing flies apart. And so the instability just has to do with adding and creating a geometric form that isn't as stable, and having that geometric form in the center of your atom, let's say, then it's really going to be a problem.
Become radioactive. That means the nucleus decays spontaneously. One of the neutrons.
So nothing happens spontaneously. So why would a physicist say that? Spontaneously. So this is the kind of physics you want, where they actually say there's some sort of spontaneous thing. It happened for no reason. There was no cause and effect. There wasn't some actual cause where something hit the neutron in the wrong way, and the nucleus, and caused it to break. And so you're saying there's no breaking mechanism. Now, obviously, if something's going to break, and it takes a 1 in a million, atoms break per second, or 1 in a trillion atoms break per second. I mean, you just can change the number and you change the decay rate. Wow, how odd, how unusual the event has to be for, you have to have just the right bit of force, just the right gamma ray to hit just the right spot, and it breaks. So what's complicated about that? There's nothing complicated about that. And that you could affect that rate based on motion, and lots of other things would affect it. So you could change the rate at which it decays by just changing the environment it's in, and we do that all the time. So if you take a bunch of uranium and spread it out, in your living room, no threat. Okay, you take a bunch of uranium and consolidate into a thimble, all of a sudden now it's a threat. It's going to kill you because it's going to start decaying much more rapidly.
Electrons might change into a different particle or pop off or whatever. There's a whole bunch of things.
Blah, 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 whatever. So right here, he's got it right. He's got little red things, little blue things still. Right here, everything looks just fine. But everything else is garbage.
That can happen there. And the same thing happens if you have too few neutrons. If you have too few neutrons, then you have other problems with...
Yeah, so that means you have too few electrons, frankly. So if you have too few neutrons are carrying the electron is the essential binding agent. So obviously if you have too few neutrons, you're going to have a very weak connection to your protons.
The force is holding the nucleus together, and it again becomes unstable. So for every atom on the periodic table, you have...
the idea is it's just kind of amazing that the truth is there's only a certain number, 100, a little less, of these naturally forming nucleuses. And that's it. There's that number of nucleuses, and you can have them with one extra proton or one less proton and create these isotopes, but the basic geometry is the same, and all you're doing is changing the geometry within one section of the nucleus to create the isotopes. And generally speaking, it's just kind of, you can understand that the geometry is kind of rigid, like triangle, square, circle, that there's rigid geometry. And the rigid geometry says there's only a certain number of arrangements of this stuff that can be symmetrical and functional, that can survive outside of the sun.
Have a finite amount of protons for the identity of the atom. And you have to have some range of neutrons to actually have enough strong force to hold it together. And these are the isotopes that you might have heard about, carbon-12. Then you have...
So it's kind of easy to understand the 13 and 14 just being made out of, you're just taking one of those dice, you're making it out of dice, little square dice, and you take one of the dice and, you put an extra proton in it. Yeah. And now that dice is less durable, let's just say, and makes the product capable of exploding.
Carbon-14. The numbers at the end are referencing basically the different number of neutrons that are in there. And if you have too many neutrons, it's unstable, and if you have too few neutrons, it's also unstable.
So we could just say it's a proton, but whatever. Whether there's too many protons, whether you have an extra proton or whether you have an extra neutron just means whether you're dragging an extra electron into the game or not. So I'd say that doesn't, Anyway, so I think that's all I wanted to get out of this, was just his definition of this magical strong force, when it's just so obvious that the force pulling protons close to each other is just the same charge force that does all the other moving of protons. You move protons with electrons.
And what I mean by that is it's radioactive. All right, and so you hear about uranium-238 or plutonium and different isotopes and things like this. And those again...
And again, the simple argument is it's just one of those things. So it's not like there's one on the outside that's, you put an extra proton and it's somehow floating around the outside and that made it radioactive. What makes it radioactive is that some core pile of it, some core helium nuclei has that extra electron, and that's what's making it radioactive.
Are isotopes that are necessary for the nuclear reaction to happen. Because what you want is something that's a little bit unstable that you can sort of control the reaction.
Right, and you control the reaction by controlling its half-life by forcing it to change its radioactivity, its likelihood of exploding. So you're changing its likelihood of exploding. So it's just kind of silly to say you could make an atomic clock and you can't change time. So again, they tell you that there's time dilation and all this other mush, but they don't really tell you the clock they're using has this obvious defect where I can change how fast it's going to count time, because I can change through environmental circumstances when that isotope is going to decay. And the fact is I can change it. Environmental circumstances will change it. So it's just kind of silly to say it's an indestructible clock. Well, anyway, that's a whole nother pile of mush subject. It's just all, this physics is so wooey and silly and under evidenced, and I am frankly just amazed that you all fall for it. I mean, it's just a new religion. It's just why are people attracted to vacuous explanations, magical explanations? Why? I don't get it at all. This has blighted my entire existence, living in a world full of people talking shit. I don't understand why you like to eat that shit. Why are you poo eaters? Ew. I don't get it. There's no point in me saying it, but I don't get it. I don't get you people at all.
I'm going to talk about how exactly the chain reaction happens in just a second.
All right, so it's not going to talk exactly about how it happens, but anyway, obviously when you diffuse the atom, you rip apart some other little pieces and they fly off very fast because, as pointed out, the two protons are in a circumstance where they're way closer than they should be, and they're going to fly apart at a huge velocity. And so they're going to hit other stuff and break other pieces as they do that, and that is all of the shrapnel bullshit. That's the way the bomb sort of works, is it's broken off some pieces. Those pieces hit other nuclei, cause them to cause a bunch more of this little fragments flying around, and the more fragments flying around, the more nucleuses that are in trouble. And that's the chain reaction. So anyway, enough of a blah 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 blah, and we'll call that a video. So maybe I'll I don't know what to, there's there's all these subjects. This is pretty much the strong force subject, but obviously there's a lot more to the subject than just talking about the strong force. It's about this elemental understanding of what a neutron is, and how the basic physics of the universe is the interaction between electrons and protons. This simulation, this is the only real universe. All the other stuff we interact in is this doing stuff, gazillions of events creating every second of our existence. So, but this is the only real, this is the real empty space with the real force in it, with the real elemental matter. That's the only universe that actually is, and everything else, is just a bunch of complexification of that stuff we can't see because of the vast density of it. It's so insanely, there's so much of that in every fleck of us that we lose sight of that reality, the forest and the tiny little trees. But all the trees are all there. Those are the trees. We're the gigantic green mountain, but well, anyway, no point in going over it. But it's just sensible as a philosophical position to understand just how we're just a byproduct of a mechanical system and these simple mechanical rules. And there's no magic. Everything has to be caused by a circumstance in that universe. All right, till the next time and such and so forth and whatnot. God, hate living among you. I just hate it.